Let's review the binary operators that are available in the C language. We also call these sometimes the bitwise operators, and we have 6 of these operators. We have the bitwise AND, which is a single ampersand. We have the bitwise OR, which is a single bar or pipe. We have the bitwise complement, which is a tilde. We have the bitwise XOR, which is the up caret. So this is not a power. This is an XOR. This is a bitwise XOR. So this is not exponent. Then we have the shift left operator, which is 2 left wakas. I've heard people call them wakas because they're like Pac-Man mouse, waka, 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 right? Something like that. And we also have the shift right operator, which is 2 right wakas. The bitwise AND operator, ampersand, works like this. Here's our truth table. If I have A and B, 0 and 0 is 0, as is the case for all of them. The only time that the bitwise AND operator is true is if both of the inputs are 1, right? And remember, these work bitwise on entire values. So here I've got 2 nibbles that represent 2 different values. I've got, 10, and I've got 12. So this is the value 10 and the value 12 in binary. And when I AND them together, we do it bit by bit. So the lowest 2 bits are compared using AND. 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. And 1 and 1 is 1. So we end up with a result that looks like this. Now you'll see the ampersand used a lot in low-level manipulation of embedded systems because we usually do what's called masking. This is how we check to see if a bit is set or a set of bits are set in a particular value. So in this case, I've ANDed with a mask that only has either 1, 1 or a series of 1s in it, and wherever a 1 in my input occurs, I know I'll always get a 1 there. So I can see if there's a 1 in this location or not. Same for that one. So I've got a 0 in that location. My mask has a 1 in it, so I got a 0 there. All the others, because they're zeroed out, will always be 0. So this is how we check. We can check and see if a particular bit is set in our in somewhere in memory. Things like that. The bitwise OR works similarly. If any of the 2 bits are set, then the bit itself, the output bit, will be set. So again, in our example, 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1, and 1 or 1 is 1. So we end up with a value that looks like this. The bitwise NOT is also known as a complement, and basically it just flips the bits in place. So here I've got the complement of the value 10. If I flip these bits, I get 1, 0, 1, 0, and that is pretty straightforward there. Every time there's a 1, I flip the bits and I get a 0, right? And this is not the same as the NOT exclamation point one. That's a truth check. So anything that's not 0 becomes false, and anything that is 0 becomes true. In this case, the individual bits are flipped using the tilde operator. Bitwise XOR works like XOR. Or it's the same as OR, except 1 XOR 1 is 0. So if both of them are 1, it becomes 0, right? So here, if I do 0 XOR 0, I get 0. 1 XOR 0 is 1, 0 XOR 1 is 1, and 1 XOR 1 is 0, so my value ends up looking like this. And finally, the shift left and shift right operators. The way these work is if I have 2 values, say I have a value A, and I want to shift it left by 3. So 3 is the number of positions we're going to shift the value 3 or the value 6 by. So the pattern here for 6 is 1, 1, 0. So that's the value 6 in binary. I've got a variable B that I'm going to put the shifted value into, and I'm going to shift A left by 3. And what happens is all of the individual bits are moved 3 locations to the left, and zeros are shifted into the end. So I'm going to shift 3 zeros in. That'll give me 4 zeros in the lower nibble, and my upper 2 ones end up in the next nibble of the byte, and that gives me the value 48 in this case, right? Now, look at the relationship here. 6 and 48, right? 6 and 48. So 6 times 8 is 48. 6 times 8 is 2 to the 3. So what we've effectively done is multiply by the power of whatever number is there. So the shift left operator, this is usually a single cycle operation in embedded systems inside of any processor. Actually, it's usually built into the processor, and I can do a multiply by a power of 2 using this shift left. That's a very powerful thing. It's also very fast. Usually multiplications are not nearly as fast for an arbitrary number, but if I can break it down into a power of 2, I can do it in a single cycle, a single instruction in the processor, which is actually really powerful. Similarly, for shift right, here I've got a pattern. I'm setting A to 38, which is this value here. I'm setting B to 0. That's my storage place, and I'm going to shift this one right 2. So the same thing happens here. We shift right, shift zeros into the most significant bit instead of the least significant bit, and shift everything right 2 bits. And I end up with something that looks like this. Now, this guy got shifted right 1 bit, got shifted right 2 bits, so it gets chopped off, so it's gone, right? Now this value, similarly, is the value 9. I've got 8 plus 1. 38 and 9. Those are not super related, but what it is, just like the other one is a multiply by a power of 2, this is a divide by a power of 2. So here we're dividing by 4. 38 divided by 4 is 9. It's not really, it's 9.5, but because we shifted that 1 bit off of the end of this, we lost it, and now that 0.5 is gone. So it's an integer division. We're dividing by a power of 2, and we lose whatever the fractional component is because it just falls off the end. So this is, again, another powerful thing. Divisions usually take way more operations to complete than just a shift does. So if you can do, if you need to do a divide by a power of 2, any of the powers of 2, you can do it in a single cycle using the shift right operation rather than having to do a regular divide, and that'll actually go way faster if you're trying to optimize code that uses these things.